Hi, this is Professor Fernandez. We're going to work on Class Notes A in Lesson 15. The objective here is to solve this system of two first-order linear ODEs. And I'm going to scroll up a little bit, remind you about how that goes. So what we're going to do is we are going to consider this x dot equals ax system in general. And in this part of the notes, I argued that if you take the very silly case where A is a 1-by-1 matrix, you get this first-order linear ODE that we learned how to solve in the very first lesson of the course. The general solution looks like this, and that was motivation for us to consider this trial solution to the original system up here. I worked through over here what happens if you consider that trial solution. And long story short, you are led to this eigenvalue eigenvector equation. So the recap is that if V and lambda are eigenvectors and eigenvalues respectively of the matrix A, then the solutions to x dot equals ax have this form. So scrolling back down now to the example that we're going to do, the first thing we have to do is we have to find the eigenvalues, find e-values, and eigenvectors and e-vectors. All right, so what we're going to do is follow our procedure from a lesson or two ago, and we will start with the matrix A and subtract lambda from the diagonal, 3 minus lambda. Take the determinant, set it equal to 0, and then solve for lambda. So 2 by 2 matrix, so the determinant is product of the diagonal entries, which is this, minus product of the off-diagonal entries, which is this, and then set that equal to 0. Okay, and then we want to multiply things out, solve for lambda, see if we can get perhaps, it's a nice polynomial that factors. So we have minus 6 plus 2 lambda minus 3 lambda plus lambda squared plus 4 equals 0. And I'm just going to start here with lambda squared. This combines to minus lambda, and then we got negative 6 plus 4 is negative 2. All right, and then this does indeed factor, so we get lambda minus 2 and lambda plus 1 equals 0. So I get eigenvalues of negative 1 and 2. All right, so now we have our eigenvalues. So let's go over here and start trying to find our eigenvectors. So the first eigenvalue that I'm going to find the eigenvector for is negative 1. And what I do, remember, is that I go back up to the matrix that I have formed and I solve the augmented matrix with that eigenvalue substituted in. So if I, let me clean things up here. If I put lambda equals negative 1 in here and in here, I would get 2 minus negative 1, so 2 plus 1. Sorry, negative 2 plus 1, that's negative 1. And then keep the 1 here, keep the minus 4 here. And then for this one, I would get 3 minus negative 1, 3 plus 1, 4. There we go. And then now I use my row operations to reduce this matrix. All right, so what am I going to do? Well, this first row looks exactly like the second row, except that the second row has been divided by 4. So if I replace row 2 with row 2 over 4, that would give me this exact first row. And then if I take that new row, row 2, and subtract the first row, I would get a matrix that has a second row, which is all 0. Great, and this tells me then that if I look at the first row of this matrix, minus V1 plus V2 equals 0. So V1 equals V2. So if I write out my eigenvector, which used to be V1, V2, it now has the same components. So factoring out of V1, I get 1, 1. And this is the eigenvector that is effectively kind of the basis or spans the set of eigenvectors. So that's my eigenvector for lambda equals negative 1. So then I'm going to go back and do this all over again for lambda equals 2. I'm going to go scroll up really quickly to the matrix that we had up here and then plug in lambda equals 2. So I'm going to get negative 2 minus 2, that's negative 4. Keep the 1. And then negative 4 over here, and then 3 minus 2, that's 1. Okay, so negative 4, yes. Great, so these two rows are exactly the same. So I can row reduce it to a row of zeros in the second row by just subtracting the first row from the second one. And then this gives me minus 4v1 plus v2 equals 0. I could solve for v1 here. I would divide by negative 4. I like to avoid fractions, so I'll just solve for v2. We get 4v1. So my eigenvector, which was v1, v2, is now v1, 4v1. Factor out of v1, and then I get 1, 4. So that is what I'm going to choose as my eigenvector. Great, so I'm going to remove all of the clutter now and talk about how we write down the final solution, or the two solutions for this system. The general solution for the system we are going to talk about in the next video. So I'm just going to stay here and eliminate all this clutter. Okay, so as we reviewed just about a couple of minutes ago, the solutions to the system, vector valued solutions, are of the form eigenvector e to the eigenvalue times t. So I have two eigenvectors and two corresponding eigenvalues. So I'm just going to put them in. So this was our v1, 1, 1, e to the, it came from the eigenvalue negative 1, so minus t. And then this was our eigenvector, oops, this looks strange up here. And this was down here our eigenvector, v2. So I'm going to put that in 1, 4, e to the, this came from lambda, this one comes from lambda equals 2. Great, so these are the two solutions that pop out of using this eigenvector eigenvalue technique for this system. In the next video, we will combine these into a general solution. That's going to require some linear algebra arguments about basis and span and linear independence.